Good morning, everyone. So, welcome to the 5-day workshop on engineering signal processing and communication using FPGA. So, the 5-day workshop will be given by the resource person, Dr. Satyasai Srinivas, Netimi. So, regarding this workshop, I thank the principal for giving this wonderful opportunity. So, welcome you all once again. Now, our HOD sir, Dr. Rashekharan, will give you a word regarding this.
So good morning, all present here. So as you know, in our department, we have continuously conducting many events like workshops, FDPs, conferences. So this is our fourth workshop in this academic year. So today the topic is engineering signal processing and communication systems with FPGA. So the presentation is going to delivered by Dr. Satyasai Srinivas, Director, Airtel, Karaikal. I thank you, sir, Satyasai Srinivas, sir, for accepting our invitation and giving presentation to our students. So actually, you see, our students, you know very well that you have studied digital electronics in your second year first semester. So only we have simulated with the help of Xilinx software. So after simulation, you don't know how to synthesize, how to download the code into FPGA kit. So these things and all students you don't know. So regarding this only today, we invited our Srinivas sir. Sir is going to give in-depth knowledge to you regarding the FPGA, how the code is implemented into FPGA kit. All those things sir is going to give. Thank you very much, sir.
A pleasant morning. Myself, Dr. Ramanathan. I feel glad to be a part of this workshop inaugural function. I join hands with the HOD and the management for the resource person, Dr. Srinivas, who has readily accepted our invitation to share his ideas and encourage the budding engineers to proceed in their area of communication and signal processing. And I hope that students will utilize the opportunity well, because many of the students have to learn hardware, because if you get core jobs, it will be helpful for you. It will be helpful for you in your career, and hardware jobs are more reliable when compared to IT jobs. I once again congratulate the entire Department of Electronics and Communication Engineering, coordinators, and the faculty members for coming forward to organize periodic events for the welfare of the students. Thank you. Thank you, one and all.
Thank you, sir. Now it's my pleasure to introduce the resource person, Mr. Netimi Satyasai Srinivas. He has received his integrated BE and ME degree in the Electronics and Communication Engineering from Andhra University, Visakhapatnam. From September 2016 to November 21, he is with the Department of ECE, National Institute of Technology, Puducherry, Karaikal, and worked as a research associate under the project titled Special Manpower Development Program for Chips to System Design, SMDP C2ST, funded by Ministry of Electronics and Information Technology, MIT. Yeah. He is currently pursuing his PhD from the same department and the same institution. From July 2020, he is working as a chair for the IEEE student branch of MITPY. In 2015, he was awarded the credential MathWorks Certified MATLAB Associate by MathWorks. You can see in 2020, he received a prestigious award titled augmenting writing skills for articulating research, along with a cash prize of 10,000 from the Department of Science and Technology, Ministry of Science and Technology, Government of India. In 2021, he was shortlisted as a semi-finalist and was ranked at 36th position of the 100 innovative solutions selected for the Swadeshi Microprocessor Challenge, innovate solutions of Atmanirbhar Bharat, conducted by MIT, Government of India. Under this challenge, he won a prize money of 1 lakh for entering into the semi-final stage. In addition, as a part of the STED challenge, he, along with his research team, comprising Dr. Lakshmi Sudha, Dr. Anand Khane, has incorporated a startup company named Ethereal India Private Limited, incubated at NITPY. He is currently serving as a director of the STED company. In July 22, he received the Best Design Award for an FPGA-based intellectual property core designed and submitted under the design contest of 26th International Symposium of VLSI Design and Test, organized by Indian Institute of Technology, Jammu. He has more than 5 years experience in FPGA-based design, digital VLSI system design. He has 9 research articles to his credit, published in high impact factor SAI journals and reputed international conferences. He has 1 granted Indian patent to his credit, and 1 Indian patent application is currently under process. He received 123 citations with an H index of 6 and an I-10 index of 5 applications. His research interests are FPGA-based digital VLSI system design, digital signal processing, and machine learning. As an introduction, I welcome you, Mr. Satyasai Srinivas, and the session is over to you.
Thank you very much, sir, for the brief introduction. And I also thank the management for giving me this opportunity to conduct this 5-day workshop. Sir, Dr. Mahesh, sir, shall we start the?
Yes, sir. Yes, sir. You can start it.
Okay, sir. So is my voice clarity is fine, right?
Yes, it's very clear.
Okay. Okay, sir. Once again, a very good morning to one and all who are present online and who are attending this workshop. So from the title of the workshop, like Engineering, Signal Processing and Communication Systems with FPGA, I will just like to give a brief overview of what are the things that we are going to cover in this 5 days workshop. So it is purely based on digital VLSI system design with a focus on FPGA based designs. So when it comes to digital VLSI, we have 2 different aspects. One is FPGA based design and the second one is application specific integrated circuit design. So in this workshop we are purely concentrating on FPGA based designs, and so for this we'll be using Xilinx Vivado as our technology node, and the Xilinx based FPGAs are to develop our custom hardware architectures and deployment on these FPGAs. So the design flow will be similar with respect to FPGA based designs. The same design flow can be adopted in order to develop your hardware circuits on a wide range of FPGAs using wide range of EDA CAD tools. So in the market, if you look into this scenario, so Xilinx, now it has been acquired by AMD. So now we call it as AMD Xilinx. So this is one of the key player in providing the FPGA based EDA CAD tools and as well as FPGA target devices. Similarly, we also have other vendors in the market. Say, for example, we have Intel. They have a family of FPGAs which are called as Altera. And similarly, we also have lattice and micro semi and many more. So whoever is providing you the FPGA target device, they will definitely provide you the electronic design automation EDA or computer aided design CAD tool in order to develop your hardware circuits on the FPGA. So moreover, the less whatever the platform which you are choosing, the design flow will remain the same. So I will be mainly focusing on the design aspects, and we will be using the Xilinx based tool. The tool name is called Vivado Design Suite or Suite. That is the latest version. If I'm not wrong, it is 2022.1. So you can install this software that can be downloaded from the official website of Xilinx Vivado. I think Dr. Mahesh will be assisting the people who are the students who are attending from the institution to for installing this tool in your laptops. So depending on the space requirements, I don't strictly tell like to use the latest version. The latest version is always advised to use in your system. But depending on the size constraints, if you do not have a required amount of space in your system, then you can go for a lower version, maybe 2021 or a 2020. So depending on that, you can choose your preferred version. But I prefer to use the latest version. So it depends on individual perspective. But more or less, there won't be much difference in the design flow. So I hope everyone have installed, or else few people are still installing. Those who have not yet installed, I recommend them to complete the installation by today itself. Today we'll be only covering the basic introduction part. By keeping in view I came to know from the organizers like third year BTech and fourth year BTech students are also attending along with the faculty members. So by keeping in view of the students, today I will be just giving you a brief introduction. So from tomorrow onwards, the hands-on sessions will be more. We will try to do as many hands-on as possible in order to get a real-time experience. So the theoretical part would be very less, and there will be more of a practical aspects. Because I won't stress on the theory part. Why? Because anyhow, as part of your academic curriculum, you might be having a theoretical subjects or a practical lab sessions. So minimum working knowledge is fine. I will be dealing with giving you an overview as per the industry standard. So what is the current industry standard and the current methodologies which are being adopted in developing the digital circuits or systems prototyping on FPGA. So those who have not yet completed the installation process, please take the assistance of Dr. Mahesh sir and try to finish the installation by today itself. And coming to, so we'll just move on to the introduction aspects. So before going into the details, I would like to give a quick prerequisite brief idea regarding few important aspects. Uh, Excuse me, sir, Mahesh sir. I'm getting a few disturbance from the different sources. So I request
Nice,
all the
clear, sir.
participants. Yeah. I request all the participants to mute their mics. So at the end, I will give you some time where you can just raise any queries and you can communicate with me as well. And over the 5 days of period, we will be in touch so we can have a healthy discussion from both sides and to resolve your queries. So let me just um, Yeah, I just want to begin with few basics so that will help you in understanding the actual concept which is behind this 5 days workshop. So for that, I'll just share my screen. Just give me some time. Uh, can Mahesh sir, can you please
Yes, sir.
confirm
Yes, sir.
whether screen is visible? Okay, fine. Okay, coming to, I will just write a few notes, sir. If you can, if you are interested, you can just take a notes, or else you can just listen to what I am saying. For the time being, I will turn off the video cam. Bandwidth, please. Okay, so let's begin. So coming to the VLSI technology, I hope the text is clear, right?
Yes, sir. It's very clear.
Okay, fine. Thank you for the feedback. So coming to the VLSI technology, so VLSI technology is a very broad field. So first we will try to understand what are the key differences or various types of sub technologies which are being offered under the major broad field of VLSI technology. So there are many types of classifications. So there is no strict rule of classifying this VLSI technology. For the ease and better understanding for today's audience, I'm just presenting one of the classification from my side. So this technology can be broadly viewed into two different aspects. So mainly there are two functional groups who are working in the VLSI technology. So for the first one, what I say it is as a design technology. So which mainly focuses on developing the circuits and or designing any kind of a circuits. So that falls under design technology. And second one, what I call it as process technology. It is also called as fabrication technology. So it mainly deals with the processing aspects or the fabrication aspects of realizing a physical device that can be placed on a printed circuit board, and a group of all these circuits on a printed circuit board will make print any maybe for example a motherboard in your computer or else in your mobile phone. So a group of all these chips which are placed on the printed circuit board. So fabrication of a single chip or else a fabrication of a circuit board on a PCB or etc. This all relates to the processing aspects or a fabrication technology. So this is a thing. So fabrication in the sense deals with the fabrication of chips as well as the fabrication of printed circuit boards or else both together. So the VLSI technology is broadly classified into two different entities, design as well as fabrication. So there are a lot of engineers who work in the design aspects. There are a lot of engineers who work on the fabrication aspects. So this is one type of classification. If you see, we are focusing mainly on the design aspects. This workshop is also mainly focused on design aspects. So we are not concentrating on the fabrication part. So that we can see later on. So my main aim is design technology. So I also belongs to the design technology field. So coming to the design technology, so what are the what are the different types of classifications which are available in the design technology? Again, here, this also can be classified into two types. One is maybe three types, I can say. One is analog design. On the next one is digital. that is pure analog, pure digital, and other one is mixed. So this is analog and digital. So again, in the design aspects, there are three differences. We have an analog design, digital design, and a mixed both analog and digital circuit design. So again, we have a dedicated set of skilled workforce in the industry who work mainly in the analog design aspect, or as a digital design aspect, or as a mixed analog and digital. So these are the three different domains where you can have a large number of job opportunities in the industry side. So again, so if you classify, uh, we can further go down into one more hierarchical level. So please see. So the main role of VLSI technology is to design a circuit. Circuit, what we call it as IC, that is integrated circuit. So analog people will try to develop ICs, mainly analog integrated circuits. So what is the technology that they use to develop these analog ICs? So that technology, in terms of VLSI term, that we call it as full custom design. So all these things, analog, digital, and mixed IC design. So we are only talking about integrated circuits. So you know the difference between what is a circuit and what is an integrated circuit. So there's a key difference. So integrated circuits is like at a micro or nano scale level. So which are packed in the form of a die and which comes in the form of a package. So that we call it as an integrated circuit. So integrated electronic circuit. So in that, if we have analog, we have analog design, digital IC design, and mixed analog and digital IC design. In the mixer, we in the same IC, we have analog component as well as digital component. So this is we also call this IC design as ASIC, ASIC. ASIC stands for Application Specific Integrated Circuit Designing. So we are mainly discussing about in VLSI technology. What they will do is for each and every functionality or each and every task, they will fabricate a chip. That chip is used for a particular application. That's why it is called as an application specific integrated circuit. Even the processor that you are using in your laptops, that is also a kind of an ASIC, but that is a general purpose processor. So it is not dedicated to any fixed application. So it is like a general purpose. So all the different aspects which deals with the functionality with respect to a computer or a home desktop, everything. So all these functionalities they have clubbed together in order to fabricate an ASIC for general purpose. Maybe a dedicated processor can be also fabricated to handle a one particular task that is maybe called as an application specific. So beyond that application, it won't work. So that's why a generic name, what we call is an ASIC, application specific integrated circuits. So in the analog domain, I told like it is a full custom design. What is a full custom design means? Uh, Here the level of abstraction is the circuit level that I will tell you. What is a level circuit level abstraction and everything that we will see. But as of now, you just remember like it is a full custom design. But coming to the digital IC design, here this is broadly divided into two different categories. So one is uh, that is a pure ASIC that we are going to design. That we call it as a tech, but the method by which we design this ASIC, we call it as semi-custom design. This is for designing an IC, digital IC. But this is in analog, we are also designing an application specific IC, but the methodology by which we design it is called as a full custom design. In digital IC design, there is also one entity that is called as semi-custom design, through which we will design an application specific IC. But in addition to that, we also have programmable chips wherein we can prototype our digital circuit in these programmable chips in order to for rapid prototyping. That is the first thing, the rapid prototyping. Second one, to verify the proof of concept. And third thing, as you for immediate deployment. Uh, in this one, the programmable chips, we have many variants, but the most popular variant is the FPGAs. FPGA is also an ASIC, that is application specific IC, but this falls under a different category of ASIC, where this ASIC is called as a programmable chip. So where it can be programmable. Again, don't misunderstand, like program means we are storing any program. This program is different from the conventional embedded programming that most of you people have dealt with, writing a C code on a microcontroller or a microprocessor, maybe assembly code in a microprocessor. But there the code is being stored in the memory in the form of an instruction set, and based on that instructions the operations are being executed. So it's deals with instruction fetch, decode, and process kind of a mechanism, but that is completely different. But here, why we called as a programmable chip means you can program the interconnects. That means the interconnects can be programmed at the bare metal level to realize your circuit on the FPGA. That's why it is called as a field programmable gate array. So in this FPGAs, you can only model the digital circuits. You cannot do any analog modeling and all, analog circuit design and all. So what are the main uses of FPGA is rapid development. By sitting at the comfort of your home, you can develop a circuit and put it on the FPGA. And within the FPGAs, you can realize a hardware circuit, hardware digital circuit, that is rapid prototyping. And verification of proof of concept. You can verify how your hardware circuit is going to work. And if the performance on the FPGA is matching with the desired requirements, you can directly use that FPGA chip in a real-time application. Whereas an ASIC, as you know, it is not a rapid development. It involves a lot of stages in order to fabricate a IC. So this here, as I've told you earlier, we have two different technologies like design technology, process technology. In design technology, a you have a number of steps where after performing all those things, you will get your final design, that we call it as a layout. That design you have to hand it over to the process technology. Then again in process technology you will have a series of steps. After processing all those steps, then only you will be getting an IC. So the manufacturing cost of developing an application specific IC is very high. It is in the order of millions, crores of rupees is involved. Whereas in FPGA, only the basic development board varies from 15,000 to advanced board, maybe 5 lakhs or 10 lakhs or 15 lakhs. So that is like cost effective. So and ASICs are only fabricated only when they are required in the form of a bulk usage. Maybe if your processor chip or else a Snapdragon processor in your mobile phone. So these are the bulk elements. Why? Because the company will manufacture mobile phones in quite a large in number. So each mobile phone requires a dedicated IC. In that case, they won't go for FPGA, they will only go for ASIC. But the beauty of digital VLSI is that you can read that you can verify the proof of concept on the FPGAs. Once the proof of concept has been validated, then you can fabricate your IC. So it helps to avoid an unnecessary cost or any loss in the expenditure. Uh, why? Because you will directly come to know the characteristics of how your digital circuit will work when you take it into the IC level by validating the proof of concept on the FPGA. So this is a more details about digital IC design. When coming to the mixed, we just use a full custom uh, plus uh, semi-custom design. So these are the design technologies that we deal with in developing the application specific ICs, or else they are developing a prototype circuits on the field programmable gate array FPGA. So in our 5 days webinar, 5 days FTP, we are mainly concentrating on digital VLSI system design, and that too we are focusing on the programmable chips, and that too what type of chips it is based on field programmable gate array. So this is a brief details of the VLSI technology. So I have covered more details about the design technology. So whatever we are having, analog, digital, and mixed. So let's also look into the process technology as well to get a brief idea for you. So for that, I have just have a material. I will make use of it to give you just illustration. So I think everyone were are aware of what is process technology. So everything starts with the using of a silicon wafer. So these are the key IC fabrication steps that are mainly followed worldwide in order to fabricate an IC. So where you're fabricating your your actual circuit is sitting on a silicon crystal. So first they will take a silicon and they have a silicon crystal processing methodology. So they will from the silicon, raw silicon, they will prepare these silicon crystals, and these crystals are cylindrical in structure. Each cylindrical structure is of 1 to 2 meters in length and 10 to 30 centimeters in diameter. And these crystal, a single silicon crystal is cut into a number of wafers, wherein each wafer or a slice is of 400 micrometer to 600 micrometer thickness. And these wafers are polished to a mirror finish using a chemical and mechanical polishing techniques. So on this silicon wafer, your actual circuit is being realized. So what are the further steps that goes into the process technology is like you have oxidation. After oxidation, it is followed by photolithography process. So after photolithography, you have the process called etching, and you have next followed by diffusion, and next ion implantation. After that, you have a chemical vapor deposition. And next, you have metallization in order to have the metal contacts. And finally, after this, the entire crystal on a single crystal may be hundreds and thousands of individual IC circuits, which we call it as a die, are fabricated. After that, what they will do is it will all these that the entire wafer is cut into small portions, and each in each segment will be having a in each die will be having a fabricated chip, right? That chip they will ultimately place it inside a packaging die, So there are many type of packages available. So ceramic package is available, dual inline packaging is available. So depending upon the type of packaging, the die, the core chip is packed into a die, and finally that will be provided by the manufacturer. So this is the overall technology. I'm not going much details into the process technology. If you are interested, you can just go through all these processing technology steps. These are available in any of the standard textbooks. So my the main reason for covering is like I want to give a broad perspective of what is the VLSI technology which is available in the current market, and different fields and opportunities for the students. So depending upon your field of interest, you might be having an interest in any particular hierarchy, what I have mentioned in the design technology, analog, digital mix, or else in the process technology. You can choose your career and you can proceed further. And one thing I have not covered in the design technology. So in the design technology, I told like analog design, digital IC design, and mixed analog and digital design. Apart from the design, there is also one subgroup that we call it as verification, because verification also plays a key important role. Why? Because after fabrication, you should also, once the design is ready, you should also ensure that your design is working fine. Why? Because VLSI is a very costly industry. Even when the slightest small mistake will incur in a huge amount of losses. So again, if you're whatever the circuit that you have designed, maybe on the FPGA or else maybe on the application specific IC. So ultimately, if it is not working as per the design functionality, then whatever you have done, entire it is a waste. So you need to ensure like whether your circuit is functioning with respect to the uh, desired input constraints, and whether it is giving you the expected output or not, that you have to make ensure. So for that there is a separate branch in VLSI technology that is called as a verification. Again, in verification there are a lot of opportunities available. Again, analog verification is different, digital verification is different, mixed A and D verification is different, and that is also comes that is also again a very broad field where you can have a lot of opportunities. So this is one broad perspective of the VLSI technology, and the other one which I'm going to talk about. So let me clear this. Yeah. So I may ask you to design a circuit. I will give you a specifications like I want a circuit which works in this manner, which addresses a particular functionality, and it has to. I will give some constraints. So this is, we call it as a design entry phase. So any VLSI design, any IC design or digital circuit design or analog or anything, it mainly starts with a design entry phase. So in design entry phase, end user or a customer will give you some specifications, and he gives you a problem statement. So from the problem statement, you should be able to address that by using by providing a solution in the form of a circuit, maybe analog circuit or a digital circuit or a mixed circuit, mixed A and D circuit, which addresses that problem by your provided solution. So this is how generally it works. So once you get the specification, so how do you start designing your circuit? So that is a very important step. So first of all, what is a circuit? What type of a circuit that a user is requesting you to design, that you need to understand whether it is analog circuit or a digital circuit. That we need to clearly understand. Let's forget about the mixed. In mixed, analog and digital, again, we have to design the analog components separately, digital components separately, and then we have to integrate both the things. So let's forget about analog and digital. Let's forget about the mixed. We just discuss about analog and digital. So, uh, what is that? Once you get the specifications, how you would proceed for designing a IC or IC? Let's talk about an IC. In digital, we may design either an IC or else we develop a circuit and deploy it on FPGA. So in digital, we have two options. We can go for direct IC design, or else we can design a circuit and deploy it on FPGA. So we will see what to do it. So, let me suppose I am the end user and I am asking you to design a low noise amplifier. So low noise amplifier, again, it's an analog component. So how do you start you designing your analog circuit? So what is the entry phase? So in the analog, as I mentioned you earlier, it is called as a full custom design. So the entry phase, what you're going to work, that will be uh, at the transistor level. This is a very important concept. Please pay attention. Uh, so in any analog circuits, whatever you are going to design, you will be designing them at the transistor level. Say, for example, what we can say. We will talk about examples later on. Okay. Uh, so the entry phase is at transistor level. So you will start building your circuits at the schematic level. Uh, Using the transistors. So say for example, in your design, it requires a mixed number of maybe some 10 to 15 transistors. Again, the transistors in the sense, it can be either BJTs or a MOSFETs or a FinFETs. That depends upon what is the type of a device that you are using for. Again, MOSFETs, you have NMOS, PMOS, and CMOS. So different, again, coming to logic families, you have many logic families. So let's not dive deep into these aspects. Let's have only a broad perspective. So you will be working on the transistor level. So what you will be doing is you will be selectively picking each and every transistor and building your circuit by using these schematics. So what do you mean by schematic is just like how you will draw your circuits in your lab, like that you will be having an EDA tool where you take some devices, uh, like this you will be interconnecting. This is called a schematic level, right? So you'll be having a transistor symbols. So by using the schematic level, that you will be taking each and every transistor, placing it as per your desired connections, as per the desired placement, and then you will be connecting everything, and you will be providing some voltage source, V in, V out, some VDD, VSS. So these things. So this is called as a schematic level. Uh, you're drawing the schematic. It is also called as a transistor level because you're working with the individual device. Device in the sense, in this case, it is a transistor. So once all this transistor schematic is everything is generated, then what you will do is you will go for layout. I think you might be aware of stick diagrams as well. If I'm not wrong, I think whether you have covered in your course curriculum or not, that I don't know. So from this, we have a concept called stick diagram. From the stick diagram, we will be drawing the layout. So again, layout is nothing but it is called as a geometrical representation of your circuit. So if you want, I can just Google some images and I will show it. Yeah. This is the layout that I am talking about. So it's a geometrical representation. So here you can see the VCC. This is a metal contact, and you have a ground in blue color that is also a metal contact, and your actual transistor is in represented in red color, that is maybe either a polysilicon or anything. Again, you'll be having a p-type substrate, n-type substrate, metal contacts, a polysilicon layer, and so on and so for metal layer, and these things. So this is called as a layout. So from the schematic, so you can see here, this is one of an example. On the left hand side, you have the schematic of a circuit. On the right hand side, you have the appropriate layout. So in this fashion, you'll be first designing your schematic, and the entry level is a transistor level. So with the transistors only, you'll be clubbing each to your designing your entire circuit, and then there are advanced tools are available. Once you design this transistor, equivalent layout will be generated. So how that layout will be generated? So that is also very important thing. How the layout is generated means we'll be having PDKs. So PDK stands for Process Design Kit. Say, for example, you want to manufacture your analog IC. So what you do is in the worldwide, there are only few manufacturers who will design your integrated circuits. Say, for example, if you are aware, TSMC, Taiwan, Semiconductor Manufacturing Corporation is a leading IC fabrication lab, which manufactures around, I think, 50 to 70% of world ICs. Like that, Qualcomm has their own foundry, and Samsung has their own foundry in South Korea. So like that, there are
Sir, you are muted, sir.
Hello, sir. Am I audible now?
Yes, sir. You are audible, sir.
Just now it is muted or long back, sir?
Just now it is
Hello?
muted.
Okay.
Just now it is muted.
Okay, fine. So I was explaining about PDKs. So PDK stands for Process Design Kit. So I told you earlier, like once you draw this schematic, you will get the layout automatically by the tool. So how the tool is going to generate this layout is, we'll be having a process design kit files. These files you will be procuring from the foundry. So foundry is nothing but it is a fab lab. So fabrication laboratory. So from the fabrication laboratory, you will get all these files. So in these files, what are the things available is you will be having a key information about layouts. So here you can see this is a layout, right? So again in layouts, you will be having a layout for metal, layout for polysilicon for forming the channel between the transistors, and layout for P-type substrate, layout for N-type substrate, layout for the contacts, layout for the implant, so on and so forth.
Hello, sir. Srinu, sir. Your mic is again muted.
Now, sir,
Now it's audible, sir.
I don't know why it is happening.
Maybe some technical glitch.
Okay, fine. So all these layouts generally follow lambda-based design rules, and so in these rules they define what is the spacing between the metal and the contact metal. What is the how much percentage of crossing should be there between a metal and a polysilicon, so on and so forth. So all this key information will be available in the process design files. So again, if you see, if you have a PMOS and if you have an NMOS, the corresponding layout files will be already available in the process design file, process design kit files. So what the EDA or CAD tool will do is, it will convert your schematic. This is a schematic what I'm talking about. It will convert the schematic to the equivalent layout by using the PDK files. So once you get this layout needs to be saved in the form of a specific format that we call it as GDS2. So GDS2 stands for Graphical Data Stream Information Interchange. So information interchange, this is called double I, but as per naming convention, they will call it as GDS2. They won't call it as GDSII, they will call it as GDS2. There is also one more file format that is called as OASIS, OASIS. If I'm not wrong, I will just Google it for you. Mostly they will use GDS, but nowadays they are using OASIS also as one of the file format. And OASIS stands for Open Artwork System Interchange Standard. So this file needs to be given to the foundry, and this file what they will do is they'll upload in the machinery, and the machinery is will handle the process technology. What are the steps I told you right earlier in the process technology? So it has various steps, right? So so they will place the silicon crystal and they will upload the GDS file. And with respect to the GDS file, it will do oxidation, it will do photolithography, etching, diffusion, so on and so forth. And finally, your IC will be fabricated. So this is the method that is being adopted in the industry standard to fabricate ICs. So again, you might be heard of.
Sir, sorry for disturbance again.
Yes, sir.
Sir, your screen sharing is being stopped. Can you please redo it?
Okay, sir. Just a minute. For me, it is showing. Okay, I will stop it and I will reshare it again.
Yeah. Okay, sir.
Now, are you able to see, sir?
Yes. Yes. Yes.
Okay. Okay. Uh, Apart from this, I think you might be also heard about the technology node. So people nowadays are talking as 14 nanometer technology, 7 nanometer technology, 3 nanometer technology. So what is this? referred to as. Nanometer technology is nothing but this is a transistor length what they are talking about. So earlier I told like what from the foundry you have to get the PDK kit. So for each and every PDK, for each and every technology node, the PDK is different. So as the transistor size is changing, the design rules will change, layouts will change. So entirely everything will be changing. So you need to decide on in which technology node you are going to fabricate your IC. So down the line, you have a 350 nanometer technology, old technology, 180 nanometer technology, 90 nanometer technology, 45 nanometer technology, and 28 nanometer technology. So the latest are mostly they are using for 14, 7, 3 up. They are only using from 28 to 3 nanometer technology. Above 28, if you are using old technology, the fabrication cost will reduce. If you are using the lowest technology node, it will increase the cost of your fabrication. So depending upon the budget and all, companies will fabricate as per their desired choice. Again, if you are manufacturing from TSMC, that file PDK files are different. And if you are manufacturing from UMC or Global Foundry, GF, or so on and so forth, the technology PDKs is different. So say for example, if you are taking 28 nanometer technology as your design node, as your technology node, the PDK for 28 nanometer technology of TSMC is different, UMC is different, and Global Foundry is different. So it is everything depends upon the foundry from which you are going to fabricate your IC, that we call technically as tape out. So from which foundry you are going to tape out your circuit, from that foundry you have to take your PDK kit by making an MOU agreement with them. And then what you have to do is you have to design your circuit and use this PDK to finally generate the GDS2 file. So this is one thing. So earlier how I started my explanation is we only saw the analog design. So in that full custom, the entry level is transistor. So that is the thing we are talking about. So transistor level. So if you nowadays, if you take into consideration a modern, maybe the Intel processor itself that is in your computer. So it has crores of transistors are available. So if you look into this scenario, analog design is fully based on full custom based model. And in full custom, you have to operate with at the transistor level by using all the schematics. So if you take an ordinary person, a single person, if he sits at least 8 hours a day, mostly depending upon his expertise, he can develop any circuit that consists of around 25 to 30 transistors. Develop in the sense, develop and fully test it and evaluate it without any error. So minimum average skilled expertise, if you take into consideration, hardly 25 to 30 transistor level complexity circuits only can be designed. But if we are talking about millions of transistors in a processor, so how these large scale circuits are developed, and you can also see the variants are coming instantly in a market within 1 or 2 months. A new variant, the now the technology advancements are happening at a very less amount of time. So within a months of time you're getting a new versions. Then how, but if you take at the if you look at the industrial aspect, the number of persons who are working on this aspect may be hardly around roughly 300 to 500 or at max 1000 engineers. So how these people are able to develop a circuit having millions of transistors? So that is the beauty of the EDA CAD tool. So for the analog circuit design, there is no other alternative. You have to directly work at the transistor level. But for the digital designs, there is a advantage like you need not struggle at the transistor level. You can work at your high level design entry phase. In the high level design entry phase, what we will do is mainly we will be using some languages in order to describe our circuit. From that language, we will try to get the equivalent digital circuit. Because of using these languages, now it is very much easy to build any digital circuit, even it is having millions of transistors. But for analog case, there are no languages to the best of my knowledge, but there are few existing languages. I came to know like very few languages, but it won't give you 100, it won't give you like 100% language to circuit mapping. Only it will address only few scenarios, but majority of the scenarios you need to still work at the transistor level itself. But our design, our FTP is now mainly focusing on the digital aspects. So in the digital aspects, if anyone gives you a specification, then what is your entry phase for your design that we need to check. So in analog kind of thing, it is that the designing is always at the transistor level. This level is also called as a bottom level. So this is a bottommost level. Beyond transistors, we don't have anything that we have from the transistors. So mostly we'll have from the transistors, you will get layout. So you can call the layout as the bottom level. So it is very difficult to work at the bottom level or the transistor level. So in the digital circuit design aspects, so how do we work? So we mainly, what we do is, we work at RTL level. So what is RTL? It is called as register transfer level. So how we work at this RTL is we use some languages that we call it as HDL. HDL is stands for hardware description languages, HDL. Description or descriptive, I just forgot, just a minute. Hardware description language. So since by using this language, we are describing the hardware. That's why it is called hardware description language. So what are the different types of hardware description languages available in industry? So we have an old language that is called as VHDL. So very high speed digital circuit. I think V stands for very large scale integration or something. Just a minute. HDL stands for hardware description language. EHDL stands for just very high speed integration circuit hardware description language. So the V itself stands for very high speed integrated circuit, and HDL stands for hardware description language. And next we have Verilog HDL, Verilog hardware description language. We also have System C. This is also one of the language which is used. So on and so forth. So mainly these are the things which are used in industry standard to work at the register transfer level. So the what is register transfer level? As you have heard, the name signifies register transfer. So mainly you will deal with transfer of data between the two registers. That is the basic concept. So how the data is being transferred from one node to another node, that you keep into the mind, and then you will try to describe the flow of data or the behavior of the data how it is being manipulated, everything that you will try to model in terms of a Verilog HDL language. In terms of a hardware description language, it can be either VHDL or a Verilog or a System C as per your desired choice. And from that, you will be trying to extract the circuit. So how you will be extracting this circuit, that we will see. So as I mentioned, we will be working at the RTL level, where we'll be writing the description of RTL using HDL language. I hope from till here it is everything clear for everyone. So from the RTL, what we do is we convert this RTL to a one step low level, so that we call it as gate level. So we'll call all these things as netlist. So from the RTL, you're writing a hardware description language HDL at the RTL level. So that language is now converted into gate level netlist. So gate level netlist, in the sense, I think you know in the digital circuit what are the basic gates. So we have AND, OR, inverter, NAND, NOR, XOR, XNOR. So total 7 basic logic gates available in our digital. So all these circuits are represented in the form of a logic gates. So that we also representing the circuit in the form of a logic gates is called gate level. So again, if you proceed one step lower hierarchy below the gate level, you have the circuit level. This is also called as transistor level. This is also called as device level. So we call it as again netlist. So again, a logic gate is nothing but if you take a inverter, that is a NOT gate. So NOT gate in the CMOS logic, if you check, you have one PMOS and one NMOS. So that is an inverter. So one PMOS and one NMOS, the combination is a complementary metal oxide semiconductor, that is CMOS configuration. This acts as a NOT gate. So if you talk about a gate level, it has a one input, one output. So if you give one, you will get zero. If you give zero, you will get one. That is gate level. If you talk at a circuit or a transistor level, the NOT gate is made up of one PMOS and one NMOS in case of CMOS logic. If you take any other logic family, again, the configuration will change. So here for case of illustration, I'm only taking into consideration only the CMOS logic. So from the gate level, we'll get the circuit level. From the circuit level or the device level or the transistor level, what we will get is the layout. From this layout only, we will get the GDS2 file. Why this GDS2 file is, it is only for fabricating the IC, that you keep it in mind. This is not the FPGA design flow. FPGA design flow is slightly different. That also I will cover in the next discussion. So mainly I'm emphasizing on IC design. So in that too, digital IC design. In digital IC design, we start with RTL. From the RTL, we'll get to gate level. From the gate level, we get circuit or transistor level or a device level. From that, we'll get a layout. This layout, when we will get is after placement, routing in the sense design routing, as well as power routing. I mean logic routing and power routing. Place before that, it is floor planning. So floor planning, placement, routing. Maybe in your maybe you're developing a system. In the system you have many component A, B, C. So floor planning in the sense you have a square shaped silicon core. In that silicon core where you want to keep the component A, B, and C. That is decided with respect to floor planning. Once it is decided, the component, each component will have its own specific layout, right? That layout will be placed. Once the layout is placed, each and every component will have interconnections. It have power connections or data connections, data bus, or any other kind of interconnections will be there, right? So these interconnections will be made via the metal wire contacts that we call it as routing. So after routing, next IO placement. And IO pad connections will be there. That is at the boundary, peripheral boundary. You will be having IO pads to that input output pads. You have to connect to your individual modules. After that, IO ring will be placed around the main core of your silicon wafer. In again, in between any void spaces are there, what we will do is we will add filler cells. I will write it here. This is only for isolation purpose. So not for any, they don't have any functional significance, filler cells. And then a final, they will give a silicon number. One more layer will be kept. On that layer they will write this silicon number. This silicon number is only for the machine to identify the circuit. Why? Because in a single wafer, I told like many circuits will be fabricated. It may be like all circuits are same circuits, or it may be like each circuit is a different circuit. Maybe if a Samsung is placing an order to fabricate XMOS processor or a Snapdragon processor on a single crystal, all Snapdragon processors may be fabricated, or else uh, in the single crystal, half of the crystal may be fabricated with a Snapdragon processor, and remaining another half vacant space is there. So fab labs, they want to fabricate by leaving a free space on the wafer. They will tightly pack all the circuits, then only they will fabricate. Otherwise, it will create a loss for them. Again, if any leftover space is there on the wafer, then what they will do, if anyone is giving any order, maybe MediaTek is giving any order, then they also place that MediaTek related circuits on that one, and then they will fabricate. Finally, when they cut once the circuit has been fabricated on the wafer, then they will have to cut it, right? So they have to cut and take individual component chip. So how the machine will identify what type of a circuit this one? Whose circuit is this? Whether it's a Snapdragon's circuit or is a MediaTek circuit. So for that, they will you have to give a silicon number. That silicon number will be etched on the layout. Based on that number, the machine will identify what type of a circuit. This is only for this one. So after all this information has been encoded, you will generate the GDS2 file. This you will send it. So in the digital circuit design, what I told, so the entry point you are working is RTL. So since the language is involved, it is easy for you to develop the functionality of your circuit in the form of a language. From that language, you will be having a converter where it will try to map that language into gate level netlist. So this RTL to gate level mapping, this we call it as synthesis. In the technical terms, this we call it as synthesis. So from the gate level, we will go to the circuit level or a transistor level. So if you again look here, RTL to gate level, this is called as synthesis, and this is technology independent. Why I said it is technology independent. So the description is converted into gates. So irrespective of the technology, even if you're fabricating in a NOT gate in 45 nanometer technology, or else a 90 nanometer technology, or a 28 nanometer technology, the NOT gate is a NOT gate itself. If you give one, it gives zero. If you give zero, it gives one. So the functionality is not disturbed. So it is technology independent. So after synthesis, so RTL to gate level mapping, that we call it as synthesis. So that is technology independent. Once you get the netlist, that is gate level netlist, that you are mapping into transistor level or a device level or a circuit level. This we call it as implementation. This mapping is called as implementation. Actually, in ASIC, there is no such word called implementation. This implementation, I'm just telling why, because in the FPGA, we have to do some implementation kind of scenario where what it will do is it will convert the gate level netlist into equivalent FPGA netlist. So that terminology is called implementation. But in ASIC, we won't tell it is implementation. Only for your understanding, I'm just telling implementation. Synthesis is as a in both ASIC and FPGA, synthesis is a valid keyword. That is called RTL to gate level mapping. It is called synthesis. But in ASIC kind of thing, implementation has no significance. Don't take it into consideration. This I'm only telling for your understanding. Why? Because when I tell about discuss about FPGA, then you will clearly understand regarding what is implementation. So gate level to circuit level, the transformation, I am calling it here as implementation. For the time being, you just keep that in mind. If you look at the implementation, this is a technology dependent. So it is dependent on technology. Why? Because as I told you earlier, if you want to fabricate an IC, then you have to get the PDKs, that is process design kit, in order to get the layout. Whether it is an analog design or else a digital design, an analog circuit or a digital circuit, the lowest node is a transistor. So even the analog design also has a transistor, digital design also has a transistor. The mode of operations only varies. In the digital, it will only work at saturation and cutoff, so 0 and 1, that's it. But in analog, it is we'll also not on, we won't operate in the saturation cutoff, we will operate in the other than the cutoff and saturation region. So only the mode of operation is different, but the leaf node at the bottommost node is the transistor itself. So when you're fabricating, maybe whether you want to fabricate via TSMC or else Global Foundry, you'll be getting their PDK files. So as I mentioned you earlier, you need to decide the technology node of fabrication, whether you want to fabricate in 28 nanometer technology or a 14 nanometer technology or a 7 nanometer technology, so on and so forth. So once you get a particular, once you choose a particular foundry and a particular technology node, you will get a dedicated PDK for that foundry and that technology node. By using that only, you have to generate the layout. First, you have to generate the circuit level netlist. From that circuit level netlist only, you will be getting the layout. So the gate level netlist to circuit level netlist, whatever you're mapping, that keyly depends upon the technology. So with respect to the desired technology that you want, so with that only you have to do the transformation. So that's why it is called technology dependent. So what is there on top of RTL? So as I told you earlier, in the digital VLSI system design, the entry point is RTL. But how you enter into the RTL means, first user will give you specifications. So user specification. This user specification, this what you do is, this specification you will try to partition in terms of system. The top level is the system. From the system, you will divide the system into a various number of subsystems. Now, for each subsystem, you will develop a RTL, Verilog code or a VHDL code. From that RTL, you will get the gate level netlist. From the gate level, you will get circuit level. From the circuit level, you will get the layout. This is in the case of IC design, digital IC design. So earlier I told I am the user and I am going to give you the specifications. And I told like your entry point is RTL. So how do you enter into RTL means first from the specifications, you will identify what is the system. From the system, if you are able to partition it into a number of subsystems, then it is very good. Because it is very difficult to prototype everything in the form of a single system. Always we have to partition it to the maximum possible extent. Try to divide it into as many number of subsystems as possible. After dividing it into subsystems, then what you have to do for each and every subsystem, you have to enter into the RTL phase. And in the RTL phase, you have to write the HDL code. From the HDL code, then you to perform all these operations, gate level, circuit level transformations, and then finally get the layout. At the layout, what you have to do is you have to club the layouts of all the subsystems together to form the big system. So the layout will be for the entire system. You can also generate layout for the subsystem in only those cases where you want two different ICs separately on a printed circuit board, and these will be communicating uh, outside. Means IC will send data to another IC, IC to IC communication. If you want everything to be included in a single IC and communicate and give the final functional output, then everything you need to combine in a single layout, and that entire layout you need to package in the form of a single IC chip. Then what you have to do is at the layout phase, you have to interconnect all these subsystems to form the major system. And a layout of the major topmost system, for that you have to generate a GDS2 file. So this is a typical ASIC flow. This is another perspective. But our 5 days workshop is mainly concentrated in and around FPGAs. So FPGA is also one of design flow. So as I mentioned you earlier, so if you take digital VLSI system design, you can either design via two different approaches. One is application specific IC, other one is FPGA. So you can design a standalone digital VLSI system design that is deployed on FPGA, and you can still use it in a real-time application. Or else, even if you are interested to fabricate an dedicated IC, digital IC, the first step is what they will do is they will go for deploying it on FPGA, do characterization. After that, they will go to the ASIC design flow, and then they will make an IC and they will fabricate it and use it in the application. So we are mainly focusing on FPGA based design. So in FPGA based design, again, what I said you earlier, the design phase for the design entry phase in the digital VLSI system design is RTL. So this you will be describing by using HDL. Again, on top of RTL, what you have is user specifications. This user specification, you will divide it into system. This system, you divide it into subsystems. Actually, this all comes under specifications only. From the subsystem specification, you try to write RTL. From the RTL, again, here you will write gate level. You will transform into gate level netlist. This transformation, what we call it as synthesis. From the gate level, actually, in the ASIC, we have seen from the gate level, we go to circuit or transistor level. We have a transistors, but if you take into consideration the FPGA, in FPGA we don't have transistors. We don't call them as transistors. We call it as configurable logic blocks, that we call it as CLBs. What is CLB means? As of now, you just understand it as basic building blocks. ultimately all the digital circuits are made with transistors only, but this is not the direct transistor level. In between the transistor level and the gate level, you assume like there is a one more level. This level is not present in the ASIC design flow, but this is present in the FPGA design flow. Why? Because as I mentioned you earlier, what is FPGA? It is field programmable gate array. That means programmable gate array, you're programming something. What you're programming? You're programming some basic building blocks. As per FPGA convention, what are these basic building blocks? These are called as configurable logic blocks, that is called as CLBs. So this gate level netlist to CLBs, this we call it as implementation. After this implementation, what we do is, in the ASIC, we have seen from the circuit level, we developed a layout. But again, here we don't develop any layout. After transforming into the configure, after transforming into the implementation netlist, this we call as implementation netlist. Then what we do is here also some placement routing, everything will be there as we have discussed in case of ASIC. We have placement routing, everything, but these placements are nothing but selection of CLBs. So we have a big chip. In big chip, we have a number of configurable logic blocks. The tool will design the optimal CLBs which are required to realize your circuit. So optimal selection, that is called floor planning. Next, placement. So which module should go into which CLB, that is called placement. Again, interconnection between all these CLBs, that we call it as routing. This is electronically programmable, right? So electronically you're programming and you're programming the interconnects. So the CLBs will be get programmed and they will interconnect with each other with respect to the desired circuit. And where all these things needs to happen inside the FPGA. The FPGA again is physically divided into a number of banks and sectors. Each banks have dedicated IOs which are surrounding the periphery boundary of the FPGA. So what it will do is there are so many number of optimization algorithms that will run at the background. They will only choose, you need not struggle anything. The tool will select the CLBs, optimum CLBs, in order to perform optimal routing, in order to reduce the transmission delay between one signal node to another signal node, so on and so forth. So gate level netlist is transformed into CLBs, and this we call it as implementation. Now, finally, this needs to be programmed, right? So for programming, we need a file that is called as a bitstream file generation. So a bitstream file is generated. Once this bitstream file is generated, we will use this bitstream file to program our FPGA. So the bitstream file will load into the FPGA to realize your digital circuit on FPGA. And depending upon the functionality, your circuit will behave on the FPGA. So this is a key difference between ASIC design flow and the FPGA design flow. Uh, both have RTL phase, gate level description, but in case of ASIC we have gate level to transistor level, but in case of FPGA we have gate level to CLBs. In ASIC we have transistor level to layout. In FPGA we have CLB to bitstream. From layout, we'll get GDS2 file that will send to Foundry in case of ASIC for IC fabrication. But in case of FPGA, the bitstream file what we are getting, we don't send it to anywhere. We will just dump it in our target device, and then we will realize our circuit within seconds on the FPGA. In case of ASIC, you send it to fabrication lab. Fabrication lab will do fabrication. They will test it and they will send you after some months of after you give some order. Then you can use that in your custom made PCB and you can operate it. So this is the overall design flow. Now Since we are dealing with FPGAs, it is mandatory to understand the internal architecture of FPGA. So again, this is a very vast topic. In the interest of time, I don't cover more deep details. I will only give only the broad perspective. I request the audience to just go through some any of the standard reference textbooks to understand about the architecture. So coming to the FPGAs, depending upon the class, family, vendor, everything, the number of the specifications of one FPGA to another FPGA will vary depending upon the manufacturer of the company or the or what is the class of family or architecture which they have adopted. But in general, FPGAs, they the basic building blocks, what we call as CLBs, this is called as configurable logic blocks. So internally comprises of CLBs. Again, if you go one step hierarchy down, so if this is a CLB, so what does a CLB contains? It consists of slices. Again, there are two variants of slices. One is slice L and other one is slice M. Slice L is used to develop a logic. Slice M is used to develop distributed RAM. Okay. Again in slice, again if you go one step a hierarchy, what you will be having is you will be having lookup tables, LUT. So each lookup table has a fixed configuration, fixed set of inputs and fixed set of outputs. This configuration varies with respect to one FPGA to another FPGA. Some FPGAs will have 4 input to lookup tables or a 6 input or a 8 input. So that varies depending on configuration. So for example, I'll just Google it for you. Yeah, this is one of the figure illustrating. I will enlarge it. Yeah, you can see here what I mentioned, CLBs. So if this is the FPGA chip is square in shape, inside FPGA you have configurable logic blocks. This we call it as a basic building blocks. And one CLB to another CLB interconnection, that is actually by default they are not in connected, but electronically programmable. If I told you like it is field programmable, right? So once if you program, you can interconnect the CLBs from one CLB to another CLB via the switch matrix. So switch matrix is also one of the uh, component inside the FPGA. So at the outer boundary of the FPGA, you have IOBs, that stands for input output blocks, through which you can give, there will be dedicated pins allocated to for input and output, uh, which acts as an input and output peripherals. Next, if you see the structure of a CLB, that also I will just show it to you. Give me a minute. Yeah, this is one of a typical figure. This is a structure of a CLB. Here you can see a 4 input. This is a CLB configurable logic block. Here you can see a 4 input lookup table LUT and flip flop, and you have a mux, and you have one output line. Just a minute. Let me show any other architecture. Yeah, this one. So this entire outer box, what you are saying is CLB. Inside CLB, you are having here in this figure two slices, slice one and slice two. Inside this slice, you have here two lookup tables, one each of four input lookup table and one output, and you have one carry logic. After that, again, you have two flip-flops in a slice, and these are the outputs. So the configuration will vary depend on the FPGA, so that you need not worry. So whatever the FPGA that you are taking, you can just read the data sheet to get the information about the internal architecture of a slice. So internal architecture of a CLB. So mainly you have this is a CLB at the top. Inside you will have slice. If the slice is used for logic, it is called as slice L. If it is used to as a distributed RAM, then it is called slice M. So if it acts as a memory, it is called as slice M. Which is for a logic, it is called slice L. So inside each slice, you will have a finite number of lookup tables. So each lookup table is of again has finite number of inputs and a single output. So I mean to say, what is lookup table? I think everyone able to understand. If it is a two input lookup table means you have two inputs. So two inputs means how many combinations? Four combinations. And one output. So this is A input, this is B input, one output. This output logic depends on the functionality, whatever your functionality is. So mainly what it will do is these combinations will be stored in this lookup table, and whatever the input is coming, depending on that, the respective output value will be there, right? So the output value is fed out on the lookup table output. Again, all these lookup tables you have seen right here in the maybe it is connected to some carry look ahead logic. After that, you will have some flip flops. Before that, I think you'll also have here they have not shown multiplexer. Actually, multiplexer is also available. So the multiplexer, what it will do is it will either take the lookup table output or else the flip-flop output. So let me show if any figure is available in the Google. Even multiplexer is also available. Let me check. Yeah, this is one type of configuration where you can see. So there are a lot of configurations available, but mostly the building blocks. If anyone asks you what are the basic building blocks of a FPGA, we call it as CLBs. And what are the components of CLBs means you will have slice. After inside the slice, you will have lookup tables. Again, you have carry look ahead logic. CLA logic, carry look ahead logic. Next, you will have some flip flops, and next you have a mux. That's it. So this is a typical FPGA, but modern FPGAs, if you take into consideration, so not they are not only comes with the CLBs. There is a file. Just a minute. Yeah, earlier first we have discussed about this figure, right? So in this figure, you can see what they have shown is that the FPGA is completely made up of CLBs. So and switch matrix, but this is not the case in the modern FPGAs. If you take into consideration, it has CLB switch matrix. In addition to that, it also has some dedicated resources. To name a few, one is block RAM. we call in short as BRAMs. These can be configured to realize RAM memory or ROM memory. Why these are very much helpful is like if you take as you know that FPGAs consists of configurable logic blocks. These are the basic building blocks. These blocks can be used to develop logic. It can act as a logic or else it can act as a memory. Say for example, in your design, you have a lot of a logic load as well as a memory load. So if you're using the CLBs in order to realize the entire logic as well as use the CLBs to fulfill the requirements of your memory, then the utilization of CLBs will be very huge, and sometimes that utilization exceeds beyond the number of resources available within the FPGA. In that cases, you cannot fit your entire digital hardware architecture on the FPGA. If your design requires more number of resources, then you have to go for a high range of higher version of FPGAs that provide more number of resources. So if you take a beginner level or a small scale FPGA, you will have a limited resources of CLBs around 35,000 or 20,000. If you take a most advanced version, you will have 1 lakh or 2 lakh number of resources. But if you use all these resources for both logic and as well as a memory, the resources will be exhausted or it will be utilized very quickly, and you won't get any space to main concentration is to put your hardware circuit, right? You won't get any place to put your hardware circuit. That is the reason why modern FPGAs, what they have done is they have introduced dedicated modules for block RAMs. So whatever the memory overhead or memory requirements is needed for your hardware, that can be specifically realized by using BRAMs. Thereby, it reduces the load of realizing a distributed RAM using the configurable logic blocks. Then the logic blocks will only be used for realizing the logic, but not for the memory. In that case, you can save the number of resources. So another main important resource that is available on the FPGAs nowadays is DSP blocks. In terms of Xilinx, they call it as DSP48E. This is called as this is used to perform arithmetic operations, like mostly the addition, subtraction, multiplication, so on and so forth. All these arithmetic operations. Again, if you take a half adder or a full adder into consideration, again, if you take a half adder, you have an XOR and you have an AND. So these are two gates, right? These can be modeled, mapped into the lookup tables of or CLBs of an FPGA to get a sum to realize a half adder with sum and carry by using the resources of CLB. This is only for 1-bit adder. Maybe if you have a 64-bit full adder, means the equivalently the number of resources in the CLB utilization will be significantly high. Again, if you want to save all these resources, maybe say for example for a 64-bit for example, I'm saying for implementing 64-bit adder, say for example, some 20 CLBs are used, but you want to save the utilization of CLBs. Then in the FPGA, if you have a DSP48E slice, then you can configure this DSP48E slice to perform your arithmetic operation. In that case, one DSP unit only will be used, and you will be having a savings of 20 CLBs, where this 20 CLBs you can reuse for developing, for realizing additional hardware, other part of the hardware that your circuit requires. So in this way, you can plan everything and you can do it. In another higher version FPGAs, you also have a dedicated hardwired shifters. Shifter logics are also available where you can perform the shifting operations on the data. So these are the additional resources the modern FPGAs are providing in addition to the configurable logic blocks. So this is one thing. Now, the final aspect that I want to deal before going into the actual FPGA design. So what is the key difference between FPGA microprocessor and microcontroller? Because a lot of people will have a big confusion between FPGA microprocessor and microcontroller. Just give me a minute. Yeah, I think in your academic curriculum, maybe you might have worked with 8085 microprocessor, and you might be working with many microcontrollers like Atmel, Raspberry Pi, or Arduino. Now I am in this web FTP. I will be covering about FPGAs. Mainly, we are dealing with a Xilinx FPGAs. So what is the key difference between all these things? So a lot of students will be having a confusion between a microprocessor, microcontroller, and FPGA. One common aspect between all these things is all these three platforms is programming. So that is the biggest reason why students will get confused all the time. So they treat it as like a programmable devices, but microprocessor, microcontroller is far different from the FPGA. So how do we proceed? Yeah, microprocessor and a microcontroller, if you take these two into consideration, they fall under the class of embedded systems. And FPGA is pure VLSI. Uh, and and here you are using the programming mainly in these two things. Just a minute, I'm getting a call. Yeah, sorry for the disturbance. So coming to the programming aspects, yeah, I am talking about. So mainly microprocessor and a microcontroller falls under the category of embedded systems, and FPGA is a pure VLSI. Here, in case of microprocessor or microcontroller, you are programming at the application level. Mainly, you are focused on running your application on the available hardware resources. So at this application level, mainly you are using C language, or else yeah, mostly you're using C language for most microprocessor microcontroller. This may be converted using a compiler on an assembler into assembly language, and so, or you will have converters. So at the bottommost node, it will only understand a machine level language. So from the assembly, it may convert into machine level language. And this instruction codes, whatever the program C level language to assembly to machine level. So finally, it's nothing but an instruction code, right? So this instruction code or the executable code, that what you're doing is you are programming it into a memory, but this memory is nothing but program memory. So where you are dumping your program, and once the microprocessor or controller starts, it reads all the instructions by fetching from the program memory. It fetches, executes, and performs operations, and gives you the output. But where are these operations are being carried out? If you take a microprocessor, it has a dedicated architecture. uh, it has a fixed dedicated architecture. Even if you take microcontroller is nothing but a combination of microprocessor and any other input output peripherals. So what it is doing is it has a fixed set of architecture at the bottommost level. So whatever the programs that you're writing in the application level, they are running it. It is running this entire program instruction by instruction in a sequence of order, and all these instructions are evaluated on a dedicated hardware which is sitting at the bottommost node. So again, if you take I think you might be aware of what is the underlying architecture of 8085. I need not elaborately tell. So with that fixed architecture only, your entire application is running. So the performance of application is limited with respect to the architecture. So you don't have any controllability in changing the internal hardware architecture. The manufacturer is giving you the hardware. Only thing is you are writing a software application and deploying it, where a software application is using the underlying hardware architecture and then running your application. But whereas in FPGA, you have a dummy logic uh, where you are building your own hardware architecture uh, as per your to meet the requirements of your application. So here you're working purely on the hardware aspect, means you're purely designing your hardware from scratch, and you're running your application purely on the hardware, that is FPGA. There is another kind of a chip that we call it as SoC, that is called system on chip, where this has an FPGA as well as a processor, maybe ARM processor and anything. This we'll see in the fifth day, last day of the session. Where on the processor, again, you will write the embedded application C language. On the FPGA, you will design your custom hardware architecture. From this processor, what you do is you send the data to the FPGA. FPGA will it's an underlying architecture that is designed by on your own. So accordingly, it will perform operations and it will give the outputs to processor, and processor will take those outputs. So this is a kind of SoC design. So my main thing that I want to highlight is, don't look FPGA as a programmable device. Though it is a programmable device, it is a VLSI based designs being carried out using FPGA to build hardware circuits, and that hardware circuits is nothing but custom hardware circuits as per the user's desired specifications. Where here in the FPGAs you have full controllability in developing your own hardware architecture, whereas in microprocessor and microcontroller, the hardware is fixed and you are developing your code and working at the application level in software domain. Again, one of the beauty of FPGA is the entire architecture of a microcontroller or a microprocessor you can realize on FPGA itself, and then you can use it as a processor or controller. So this is a key difference between FPGA, microprocessor, and microcontroller. So in this session, I hope I have covered all the prerequisites which are necessary in order to start our journey, 5-day journey in the FDP, to get a hands-on experience on FPGA-based digital VLSI system design. So what are the prerequisites that I have covered? I request all the participants to keep in mind. Now we will take a lunch break, and maybe at around 3 o'clock or so, I think Dr. Mahesh sir will intimate. At that time, we will log in and we'll proceed with the second session of today, where we will start a quick hands-on with a basic introduction to Vivado design flow. And we will, if time permits, we will see small designs in the small designs that we will be developing using Verilog HDL language, and we'll try to prototype it on FPGA. That's it from my side. If anyone has any queries, they can ask.
Sir Srinu, sir.
Yes, sir.
Hello.
Yes, sir.
Sir Srinu, sir.
Yeah, tell me, sir.
Okay, sir. Then I will inform all the participants so that the next session will start at 3 o'clock.
Okay.
So we will continue at 3. Okay.
Okay, sir. Sure.
Okay. Then we take a leave. Sir.
Okay. Okay.